Welcome to The Explainer, where today we are diving into a breakthrough that could completely change the game for AI efficiency. And believe it or not, it all boils down to one simple, absolutely brilliant mathematical trick.
So let's just jump right in. What if you could run the most powerful AI models out there, but use just a tiny fraction of the memory they usually need? What if those super long, complex conversations with an AI could suddenly become way faster, way cheaper, all because of one single clever idea? Well, that's exactly what we're going to unpack today.
But to really appreciate the solution, we first have to get our heads around the problem. And right now, one of the biggest and honestly often invisible bottlenecks that's holding AI back is, well, it's its own memory.
Okay, so let's start with this core concept called the KV cache. The easiest way to think about it is like an AI's short-term memory, right? When you're chatting with someone, you don't go back and reread the entire history of your conversation just to figure out what to say next. You just remember. The KV cache is exactly that for an AI. It's what lets it keep track of the context without starting from scratch every single time.
But, and this is a huge but, here's the catch. That short-term memory, it's not infinite. With every single word you type, every single token the AI processes, the KV cache just gets bigger and bigger, and then bigger still. If you're feeding it a long document or you're in a really extended chat, it becomes this gigantic memory hog that slows everything down to a crawl and makes the whole process incredibly expensive.
So the obvious solution seems to be, hey, let's just shrink it, right? And one of the most popular ways to do that is a technique called quantization. But this idea, which seems so good on the surface, it comes with this really nasty hidden cost. Let's take a look.
The goal of quantization is pretty simple, really. You take these big 16-bit numbers that the AI is crunching, and you shrink them way down, maybe to just 3 bits. That's a huge saving, but it's not that easy. To actually decompress those numbers and use them later, the AI has to store extra data alongside them. Think of it like a little instruction key for each block of data. And these quantization constants, as they're called, well, they turn out to be surprisingly bulky.
Yeah, and this overhead is no joke. The research paper itself points out that it can add 1 or even 2 extra bits for every single number you were trying to shrink in the first place. So suddenly, your amazing 3-bit compression is actually closer to 4 or 5 bits in reality. A huge chunk of your savings just vanishes.
And this is where our story takes a really cool turn, because researchers came up with a new technique to get all the amazing benefits of that compression with absolutely none of the overhead. It's called QJL. The way QJL works is just so elegant. First, it takes all the data in the AI's memory and uses a special kind of random transformation to project it into a whole new mathematical space. Then, and this is the wild part, it does something radical. It throws away almost everything about that new projection, keeping only the sign. Is it positive or is it negative? That's it. The data is crunched down to a single bit.
Now you're probably thinking, how on earth can that possibly work? I mean, you're throwing away so much data, it seems insane. Well, the secret, the absolute genius of this whole method is asymmetry.
Okay, so here's the trick. The data that's already stored in the AI's memory, we'll call those the keys, they get the full extreme compression. They're projected and squeezed all the way down to a single bit. But, and this is crucial, the brand new information that's just coming in, the query, is treated differently. It gets projected, but it doesn't get quantized. By treating the old data and the new data completely differently, this imbalance makes the math work out in this beautiful way. It creates something called an unbiased estimator, which is basically a fancy term for a mathematical magic trick that lets you reconstruct the original meaning with shocking accuracy, all without needing to store any of those bulky overhead constants we talked about. It's pure, lossless compression.
So problem solved, right? Zero overhead, massive compression. We could just end the explainer right here. But the researchers, they asked a much deeper question. Is this approach, which is amazing for one very specific kind of calculation, truly the best way to preserve all of the information? See, QJL is fantastic at one thing in particular, preserving the relationship between two pieces of data, what mathematicians call the inner product. But here's the thing, just because you're getting that one calculation right doesn't mean you're not introducing a different, more subtle kind of error somewhere else in the system.
And that subtle error has a name: quantization bias. This happens when your compression method isn't just making a few random mistakes here and there, it's consistently, systematically
pushing the data a little bit in one direction. Your average error might look great, but there's a definite skew. It's like a thumb is permanently on the scale.
And you can see the difference so clearly here. Unbiased error is like random noise. It's scattered, but it's centered perfectly around zero. Biased error, though, even if it's small, is consistently shifted over to one side. And over time, that can introduce these subtle but really meaningful distortions in how the AI performs. So, to solve this final, really subtle problem, an even more advanced method was created. And what's so cool is that it doesn't throw QJL away. Instead, it brilliantly builds right on top of it. It's called TurboQuant.
Okay, let's break this down because it's like a two-stage rocket. First, TurboQuant uses a standard optimal quantizer, one that's really, really good at minimizing the big overall error. Now, this method is known to have a little bit of bias, but it gets the big picture almost perfect. Then, it calculates the tiny bit of error that's left over, the residual. And for that small leftover bit, it brings in our hero from before, the perfectly unbiased QJL trick.
And this combination, this is the key. It uses the best possible, though slightly biased tool for, say, 99% of the problem, and then it uses a perfectly unbiased tool to clean up that remaining 1%. The end result is the absolute best of both worlds. You get incredible accuracy with practically zero bias.
All right, so we've gone through a lot of cool math, but let's talk about the payoff. What does all of this actually mean in the real world for you and for me?
The headline number is just staggering. This isn't some tiny 10 or 20% improvement. We are talking about a greater than 5-fold reduction in the memory that an AI needs for its short-term memory. A 5x compression factor. That's huge.
And the data? Well, it proves it. The original uncompressed model uses 16 bits. The QJL method gets that down to just 3. Now, you would expect performance to just fall off a cliff, right? But look at this. On these really tough question answering tests, the compressed model doesn't just match the original, it actually performs slightly better. That's the holy grail, right? More efficiency and better performance. It's unheard of.
And this isn't just some lab experiment. This means you can have longer, faster, more intelligent conversations with AI. It means we can start running more powerful models on the phones and laptops we already have. For the companies running these AIs, it massively cuts their costs. And get this, in those grueling needle-in-a-haystack tests, where you hide one piece of information in a giant document, it finds it with perfect accuracy.
Which leaves us with one final, incredibly exciting question. We've just smashed through a major barrier, one that was making AI expensive and slow. We've just made it dramatically more efficient. So the question is no longer if we can build even more powerful and accessible AI, but what amazing, incredible things are we all going to choose to build with it now?